So again, ladder friction problems are very interesting group of problems because the friction is what is very much essential at the contact, right? So good afternoon. This is lecture number 26, and we will look at ladder friction problem, which is last set group of problems that in our module 3. So let us continue with what we left in the last period. In the last period, we were doing wedge friction problem. So we have done couple of problems to understand how nicely we can draw the free body diagram, how can you employ this Lamis theorem so that you are able to handle three-force equilibrium conveniently to get solving for unknowns. Right, so that is all in that. So now let us continue with the lecture number. This is lecture number 26. And in the same module, we will do ladder friction. So this is today 5/4/2021, and let us solve the problem on ladder friction problem. So when I say a ladder friction problem, you see that I was telling you at the beginning of this dry friction introduction, a person who can climb up the ladder comfortably without any worry, and he is able to do the necessary task at the top of the ladder, provided you have a sufficient contact surface frictions. In case it is not there, you see that you cannot climb up and you cannot do the intended task. And the very important thing is the lean angle. So the ladder will be lean against the vertical wall. So what is that lean angle with the vertical wall is going to decide also whether he is able to climb fully the ladder or is not going to climb fully, partially, only partial distance only he can climb, like that. So very interesting problem. So let's solve the problem and then we'll understand the role of friction in that, right? So I'm going to draw a ladder, a simple homogeneous ladder. That means the weight of the ladder would be at its mid span, right? So this is a vertical wall, and I have a ladder, and the ladder is lean against this vertical wall at an angle 45 degrees. The length of this ladder is 7 meters. Right, so let us say the point of contact of the ladder, the floor as point A, and the point of the ladder with the wall as B. And this is a homogeneous ladder and weighs weight W. So that would be at its midspan. So this is the W load. So now the question is, if a man whose weight is half the weight of this ladder, 1/2 the weight of this ladder, climbs it, at what distance along the ladder will he be when the ladder is about to slip? So the question is, can he climb up the ladder if this is the orientation of the ladder? The man who climbs, the weight of the man is half the weight of the ladder, so W/2. So he is to climb here, and has he able to climb fully up this ladder or not is the question. So you are also given the friction of these contact surfaces. So what is the friction value? You have for the wall mu_s value at point B is 1/3, whereas mu_s value at point A is given by half. So the roughness at the floor is higher than that of the vertical wall. So this is all given. So now you have to find out whether he is able to climb up the ladder. So let us initially consider that the man would climb up till some distance, say X, from here. This distance X. And let us have that he is situated there, and the weight of the person is W/2 now, right? So this is that. So with this configuration, we will go with the drawing free body diagram and solve the problem. So let us take now the ladder alone and draw the free body diagram. So this angle is now 45 degrees to the vertical, so to the horizontal also it's 45 degrees. And I have here now two forces external. One is the weight of the ladder, another one is the person weight W by 2. And he has climbed, we assume that from here to a distance x. And the length of the ladder is 7 meters. So this is 3.5 meter and this is 3.5 meter. 3.5 meters and this side 3.5 meters. And this is point C, it's midspan, let us say. So this is point A. I would have now here a normal. NA. And the expected motion of this is what? It will be slipping to the left. So you would have your friction force here. So I will take here the friction force to be impending state, right? That is when I will be able to find x. If x happens to be greater than 7, that he could go up till the end. Otherwise, I know till what point he can go, so that it is just about to slip. So when I say just about to slip is the question, then I should take here the maximum friction force that can be developed at both the contacts. So this should be how much it is? NA by 2, because mu s is 1 by 2. And here I will have N3 or NB. And it's going to go and this is going to come. So friction force in this direction. And that value is NB by 3. So this is what is the free body diagram now, right? So in this, the weight is at a distance 3.5 meter. The weight of the ladder is at a distance 3.5 meter, whereas the person is at a distance x that we assume. So we have to find x now. So we can apply now condition of equilibrium. So already I have used my friction force here, so that I have put the maximum static friction value at both the contact points. So this is just an impending state, that impending state. So that would give me this x value. So whatever x value that I get, if he goes just beyond that x value, then this he can't go up, and then this is going to slip. That is a condition, right? So here this angle is fixed here 45 degrees. If this angle is very large and the lean angle is very small here, then there will be a chance that he can climb. So let us just find that now what is the value of x by applying condition of equilibrium. So let me just do first equation is sigma fx equal to 0. So when I do first sigma fx equal to 0, I have here NA by 2 and that's minus NB equals 0. So I get NA equals 2 times NB. That's coming from this first equilibrium equation. Next, sigma Fy equals 0. So when I apply sigma Fy equals 0, vertical force here NA and here NB by 3, and there are two forces here, W plus W by 2. So that is 3W by 2 down. So minus 3W by 2, that's equal to 0. So I would have now NB and W relationship. So if I substitute NA here, so this is equation 1, put in equation 2, and then if I reduce this, what would happen? So this is 2 plus 1 by 3 NB equals 3W by 2. So this is now 7 by 3 NB, that's equal to 3W by 2. So NB equals 9 by 14 W. In terms of weight of the ladder, I have now what is the normal at the point of contact of ladder at the wall. So this is 2. Right? So now to get x, what I should do, I can take moment about point A, one convenient point. So let me take that point as my point A. So if I take moment about point A, equating to 0, applying convention counterclockwise moment positive, I would see that this NA will not participate. So this will be participating. So here I would have W into, what is this distance? That is moment arm. So this distance is 3.5 cos 45. So W into 3.5 cos 45 degrees is what is my moment arm. And that is going to create at point A clockwise moment, so minus. The next, minus W by 2 into X cos 45 again. Cos 45. And any other force moment, you have NB and NB by 3. So NB would create counterclockwise moment. NB by 3 also would create counterclockwise moment. So one will have 7 sin 45 momentum, other will have 7 cos 45. So plus NB into 7 sin 45 plus NB by 3 into 7 cos 45. That's all equal to 0. So you can see cos 45, sin 45, cos 45, cos 45. So cos 45 is equal to sin 45. So these all terms can be removed from this. So I would have here minus 3.5 W minus XW by 2 plus 7 NB plus 7 by 3 NB equals 0. So I can now get NB in terms of W, right? NB in terms of W. So what is my NB? So NB here is 7 plus 7 by 3. That's equal to W if I take out. So 3.5 plus X by 2 into W. So this is going to be 28 by 3. So 28 by 3 NB equals 3.5 plus X by 2 into W. So NB equals 3 by 28 and 3.5 plus X by 2 W. So that's equation number 3. So equation 2 and 3 can be equated. Equation 2 and 3 can be equated. So 2 equals 3, as on left hand side it is NB. So I have now 9 by 14. Correct? That's 1. 9 by 14 W is what is equal to 3 by 28 into 3.5 plus X by 2 W. So this W goes out. So I would be able to solve for X. So that would be, so this is 2, this is 1, this is 3, this goes out, this goes, and this is 6. That's equal to 3.5 plus X by 2. So if I solve further, I have X by 2 equals 6 minus 3.5. That's equal to 2.5. So X equals 5 meters. So X equals 5 meters. So a person who weighs half the weight of the ladder is lean against the vertical wall by an angle 45 degrees, would climb only 5 meters up on the ladder of length 7 meters is what is the answer, right? So any doubt in this? So I can change this angle theta 45 degrees instead. If I give you some 70 degrees, and then if you are solving it, you check that what would be the value of X. If that x value happens to be greater than 7 meters, that means he is comfortably can climb up till point B, and then he can stay and continue working, right? So that is that this is a group of problem that can be asked under the topic ladder friction. So I will give you a homework problem and stop today's lecture. Maybe give you an idea of how to solve the problem, and we will end the class, right? So second problem again in ladder friction. See again a uniform ladder, right? A ladder which is lean against the ladder is uniform, leans against the vertical. See here. So this ladder goes up this point. So this angle is theta. So this angle, lean angle is theta. So this is on the floor. My hand is on the floor. Right. So this is point A. This is point B, free end, and this point is point C. This point is point C. Again, this is of length L. This is ladder of length L, and which weighs W. Right. So a uniform ladder. This is a uniform ladder of weight W. Right. Leans at an angle theta. Leans at an angle theta in a leans at an angle theta to a horizontal plane. This angle theta is given to the horizontal plane in the configuration, right? And it's lean against a vertical wall. This height of this wall is given. H. Height of this wall is h. The coefficient of static friction at all points are contact is mu s. If it is all known, now you have to show that if ladder is on the point of slipping, on the point of slipping, on the point of slipping, you have to show that cos theta minus cos cube theta equals 2 times mu s times h by 1 plus mu s square into L. That is question number 1A. So B is then show that if mu s h by 1 plus mu s square into L is greater than 1 by root 27, the ladder will not slip at any angle. The ladder will not slip at any angle. So these are the two conditions. So can you solve this problem as a homework problem? This is homework problem. So how are you going to solve this? What is the idea? So any problem that you should start solving by drawing free body diagram, apply those three equations, you would get the necessary expressions and you can deduce these conditions, right? So I leave it to you as this as a homework problem. Right? Any doubt in this problem? So uniform ladder L and which weighs W leans at an angle theta to horizontal and lean against the vertical plane, a support of height h. The coefficient of static friction is mu s at all contact surfaces. If that is so, show that the ladder is on the point of slipping. If this is at the point of slipping, means what do you have to do? At point C as well as point A, you should consider maximum static friction value, like in the previous problem. Then you would be able to deduce this expression. And then you can also prove that if you have in this part of this value mu s by this, so half the value of what you have here is greater than 1 by under root of 27, the ladder will not slip at any angle. So this can be proved, right? So just let me just draw the free body diagram for you so that you would be able to solve.
Sir, we'll be using basic equations of equilibrium in this also, right?
Yeah. So this is a kind of derivation, but that would be obtained once you are systematically drawing free body diagram and writing down the equation. This will automatically deduce. That's what is exercise, right? So let's just draw the free body diagram, right? So free body diagram, now see this free body diagram, unlike the previous one, you see there is a point C where there is a contact, right? So let me just draw the line diagram of the ladder. So this is ladder. So this is point A, this is point B, and point C is somewhere here. The total length of the ladder is L, right? And now see this face W and uniform ladder, so it is at its midspan, the weight will be acting down. That's W. And at point A, I would have NA. This is going to be NA. And this is mu S times NA. So the values are not given, so I have to take it like this. And then you see at point C, I would have perpendicular to this NC. And what is the direction of friction? So this is going to slide down, so friction would be in this direction. So that is this, and that would be mu S times NC. That's this friction value. Right, so these are the forces acting now in this. Again, if you see, there are only 3 forces here. So I can use the Lami's theorem and I can also go ahead with solving this problem. Though it is the dimensions, so the weight is there, I can extend and then I have to find here. So that line, if I extend, that would intersect, and this, if I put all will intersect. I can also prove this geometrically constructing. And I can do it. That's one way of doing it. There is another way is just write down this equation without combining, and then it is also going to be easier. Let me just yeah.
So Lami's theorem, it is not possible, right? Because neither are the forces concurrent or either are they parallel. So
No. See now, how many forces are there in the ladder? Tell me. So if I have
13, then we'll have 3 forces.
3 forces. So RA, RC, and W. So W is vertical, so I can extend this. And here I can have, see, since this mu s is all contact point same, that is phi angle. So I have to draw at an angle here, phi, and that would intersect both, and that is what is here dictating to go. So I can express that in terms of theta and phi. It is possible. You make an attempt. But instead of that, in such cases here, it is convenient not to combine and apply condition of equilibrium. So I'm just going to do now this without combining, without applying Lami's theorem. One can also do with that I ask you to work out. So now let's just look at what are my conditions of equilibrium equations. So sigma fx equal to 0 when I apply. I have here, it is mu s n a, and here these two are inclined, so I'll have 2 components. So one is what is this direction? So this is normal to this, and that will have to the vertical the same angle what is there here. This is theta, so this is also theta, right? That is also theta. That's also theta. So this one is along this, so this inclination is theta to horizontal. So I would have now this component to the right is mu s n c cos theta, and this nc, that's going to be minus, so minus nc, and opposite to this is what is horizontal component, so sin theta, right? That's equal to 0. So this is the equation 1. So what is my second equation? Sigma Fy equals 0. So sigma Fy equals 0 when I do, I will have NA, this vertical force NA, and I have here minus W, and I have here NC in this, and this is cos component, so it is plus NC cos theta, and this would be again inclined to horizontal theta, so I require vertical, so that is opposite, so it is plus mu s NC sin theta, right? Mu s NC sin theta. So that's equal to 0 is what is my second equation. So now in this, I can get 1 and substitute that on this. So here I have NA, NC, 2 unknown. So here I have NA, NC and W is known. So that's on this side. So I can solve this simultaneously. Right? I can solve this simultaneously. So let me get now here value of NA from this equation 2. So that's W minus NC. If I take out, it is going to be cos theta plus mu s sin theta, right? So this I can put in 1. This I can put this in 1. So if I put this in 1, in equation 1 I have NA is this, right? So mu s into NA is this now. So W minus NC within bracket cos theta plus mu s sin theta, right? So that's substituted here plus mu s NC. So NC if I take out, it is mu s cos theta minus sin theta. So that is equal to 0. So now here, what is that I needed to reduce? So look at here, I have to get cos theta minus cos cube theta equals this. So how do I get this expression? So I should not have NC, W, nothing should be there in this, right? So how do I get that is like this. So what I will do, I will take now mu s W on one side and rest all on the other side. So if I do that, because here I have NC, I can reduce this, I have to take it on the other side. So let me have it here, it is mu s times W, and if this goes on the other side, this is NC cos theta plus mu s NC sin theta minus NC cos theta minus NC mu s cos theta, right? Mu s cos theta plus NC sin theta plus NC sin theta. So here is there any cancellation term? Mu s NC sin theta, here NC sin theta, here it is mu s NC cos theta, mu s NC if I take see, there should be some cancellation terms which is missing here. 1 minute. This minus minus, if I put that here, I keep this mu s W on one side and take this on that side, other side, so that's positive. And NC sin theta minus mu s NC cos theta. That's correct. Mu s NC cos theta. is there any terms cancelling here? No. NC is there in all. I have sin theta, cos theta. I made one mistake here. See, when I substitute NA here, I have NA here, right? I have to substitute this. So there is a mu s here as well, right? So when I take this here, I should also bring this mu s here. So this mu s is common here. So I will have here. So that is why I was stuck here. So I will have here mu s NC cos theta, and I will also have here mu s square. This is mu s square NC sin theta. And you see here mu s NC cos theta, there is mu s NC cos theta, these terms goes off. So I have NC mu s squared sin theta, NC sin theta. So in this NC sin theta, if I take out, NC sin theta, if I take out, I'll have 1 plus mu s square. Is what is mu s times W. So mu s times W is equal to NC sin theta into 1 plus mu s square. So therefore, what is my weight? The W can be expressed now with this now. So that's going to be 1 plus mu s square by mu s into NC sin theta. NC sin theta. So let us call this equation number 3. So now again I can get expression W. Say we have to eliminate in this. If you look at it, is only a geometrical parameter. See this problem here, you are proving this trigonometric relation equals in terms of surface characteristics and the geometry of your system, height of the wall and the ladder length. So there is no force in this expression. So I have to eliminate that force. That is my intention. Then I have to eliminate W and NC. So how do I do that? I can do that if I apply my third condition of equilibrium, which is moment equilibrium. So let me take moment about point A. Right, point A. So if I apply that, so you have a class, you can proceed. I would complete this problem and then I will stop the lecture. So taking moment about point A equals 0, I would have now NC into this distance AC, right? NC into, let me take that as a distance AC minus, so that would be creating about this point, this NC counterclockwise moment, minus this W. I can have two components, one is along the ladder, another one is perpendicular to ladder. So if this angle is theta, and this will have to the vertical theta, this to the normal. So W cos theta into L by 2. That creates counterclockwise moment. So W into L by 2 cos theta is what is moment by the weight component. So that is equal to 0. So this solves now for NC and W relation. So I get now NC equals. So now this height AC I would be able to express in terms of this geometry height. See, look at here. I have this point, this height, this H. So from here. So what is now this AC? AC would be this distance plus this distance square, right? Or I want to represent that in terms of H. So how do I get in this triangle A, C, and say, let's say this is point D. In triangle A, C, D, I have now sin theta. So sin theta is what is opposite by hypotenuse. So equal H by AC. So AC will be H by sin theta. AC will be H by sin theta. So I can substitute that in this. No. I can substitute that in this in place of AC. So it is going to be, let me have this, NC is equal to W L by 2 cos theta into 1 by AC. So now AC is the length. So W L by 2 cos theta into H by this. So that's going to be sin theta up by H down is what is NC, right? So I require now here W here, or I can substitute this NC over here, right? So I can substitute that. So let me get now W. This I will write it in terms of W. So that's going to be 2 times NC into H divided by cos theta, L into cos theta, L cos theta sin theta. So that is equation 4. So now I have this equation 3 and 4, right? So I can substitute this and then reduce what is that I am interested in. Or it is W equal I have written. So equation 3 equals equation 4. So equation 3 equals 4 is what you get it from this. I have to write this expression instead of NCW I write because this equation 3, this equation 4. Left hand side is same W. So 3 equals 4 would give me 1 plus mu s square by mu s into NC sin theta. That's equal to 2 NC H by L cos theta sin theta. Right. So this NC goes off. So I would be able to have now the expression 2H. See this mu s goes on this side. So 2 mu s H by 1 plus mu s square. So this mu s goes up there and this comes in denominator. So I also have this L here and this terms I take it on this side. That's going to be cos theta. That's equal to right? That's equal to cos theta into sin square theta. Cos theta into sin square theta. So you know that sin square theta is 1 minus cos square theta. So cos theta into 1 minus cos square theta. So I can rewrite this as cos theta minus cos cube theta. What is on this side is 2 mu s h by 1 plus mu s square into L. So what is asked? So you have proved, right? So this is what is the proof. So now you go for the second problem. For the value of half the value of what is there on the left hand side is less than, right? Less than, or what is the given condition? Is less than or greater? What was the given problem? This we did, and this is the second problem. So here, so if you have this mu s h by 1 plus mu s squared within bracket into L is greater than 1 by root 27, any angle of theta will not, the ladder will not slip. So that you can just do it. I leave that part B to be a homework for you to work on it. And with that note, let me stop now. And it is just 2 minutes to the next period. You can leave. Let me just check now how many of you are there. Meeting. So there are 35 as of now. There might be some students left for the class. That's fine. And I have downloaded the attendance. If you have any doubts, you can ask. Otherwise, I will end the meeting for all of you. Right? You have any doubts?
No, sir. No, sir.
No. Okay. So next class, I'm going to start with module 4. So I leave it to you. So there are many problems in the textbook. But however, whatever the problem that I have solved, if you have understood and that line, if you are working, it is good enough, right? So with that note, let me stop recording.